Hello and welcome back to a video series on MAC 1105 College Algebra. My name's Sean Perry. These are guided notes number 16 in the series on section 4.1, quadratic functions. The first question asks us to graph the following four quadratic functions. All quadratic functions are going to be transformations of the parent function x squared. So we should note that this is our parent function and then note what transformations we're being asked to do. Here we have a right shift by 2 and a downshift by 1, and correspondingly left 2, up 1, right 2, up 1, and left 2, down 1. I would just like to note a quick little trick to drawing a convincing graph of the parabola, and that's by noting the following points surrounding the vertex. The vertex of the parabola is going to be the lowest or highest point on the parabola. Let's take a look at x squared real quick. We know that goes through 0, 0. We know that goes through 1, 1, and negative 1, 1. And 2 squared is 4. Likewise, negative 2 squared is 4. And let's go over one more. Going over to 3, we'll have to go up to 9. Going over to negative 3, we'll go up to 9 here. So for this parabola, connecting these dots, our vertex is at the origin. And one thing that I'll do when I'm trying to graph a parabola on a grid, as we're about to do, is I'll notice the following things. As long as we're not multiplying by some constant up front here, we're going to be going over 1 and up 1 from the vertex, then over another 1 and up 3, then over another 1 and up 5. So this pattern of increasing by an odd number, which increases by one step each time, is a great way to get your slopes right and get a quick collection of points for graphing the parabola. Let's see how that would look when we do this first problem. So let's start with the blue one. This has gone right 2, down 1. So I think it's easiest to start by taking the vertex, which normally would have been at the origin here, and taking that vertex right 2 and down 1 to make this new position of the vertex here. And then I'll go over 1, up 1, over 1, up 3, over 1, up 5, and I'll make these points. Likewise, on the other side, I'll go over 1, up 1, over 1, up 3, over 1, up 5, and I'll make these points. And once I have those points plotted, I can connect the dots smoothly and make a parabola. This is what I'm going to do to construct every single one of these parabolas, which doesn't have some leading term multiplied up front here. Because if there were some kind of leading term multiplied up front, it might increase these slopes proportionally. But if I'm just going like this one, left 2 and up 1, then I take my vertex, which was normally at the origin, I go left 2 and up 1, and I put my new vertex here. And then I go over 1, up 1, over 1, up 3, over 1, up 5, and I put those points there. Likewise, on the other side, do the same thing. And once I had those points graphed, I would connect them. For the yellow graph, we're doing the same thing just by going right 2 and up 1. And for the orange graph, I'm going left 2 and down 1. Here we have a similar question where we're being asked to use the parent function x squared to determine the graph of these following functions by transformation. So we just really have to identify these different transformations. Here, I'm going left by 5 units, and that's all that's happened. So the same over 1 up by some odd number has gone on here to plot my points. And I think plotting 5 points is usually pretty good. 3 points, you really don't see everything that's going on. Could be an absolute value for all we know. But 5 points starts to get the slopes right. And really, these 7 points will give you a really quite nice looking parabola. G says negative this whole thing. So we're going to actually flip this. And the negative sign is on the outside. So we flip it vertically over the x-axis. And then move it to the right by 5 units. So here we are. Now, instead of going over 1, up 1, I've had to go over 1, down 1, over 1, down 3, over 1, down 5, because we have, of course, flipped it because of this negative sign. Here, we're doing a simple vertical translation by 5 units, so we just take the whole graph and shift it up. And then some of our graph is going to go off the edge of the map, but we'll still just go over 1, up 1, over 1, up 3, and that gets us enough points to sort of suggest the parabola. Here, we're doing the same thing, but first we want to flip it, and then we want to downshift it by 5. So flipping it upside down, but then moving that upside down parabola by 5 units, we get the following. Now, notice that either this leading coefficient being negative or this leading coefficient being negative will result in a upside down parabola, while if it is positive, we have this sort of upward facing parabola. So the next questions are going to ask us to find the vertex, x-intercept, and y-intercepts of the parabola defined by some quadratic equation. And these will in general be in a couple different forms, but for right now, let's just note that there is one particular form we should be aware of. A parabola p of x may have the form a constant times x minus some constant squared plus some constant, where these h, k, and a are all allowed to be positive or negative themselves. Then we can say that the vertex of this parabola is going to be at the value hk. So finding the vertex often enough can be done just by putting it into this form. So let's walk through this example here. In order to find out where the vertex is, I need to analyze which constants are in what position here. Your minus h, well, we have a plus 4 here. So in order to have that be of the form x minus h, this needs to be an h of negative 4, because then we're talking about minusing a minus, which gives us this positive 4. So we switch this sign to find the x value of the vertex. The 50, or the k, well, it's plus k out here. So that's just going to keep its sign, and we have a vertex at minus 4, 50. Now, we should note, although it's not part of this question, it will be in subsequent questions, that this parabola opens up because this is positive, and therefore the vertex is at a minimum point. How do we find a y-intercept? Well, we just plug in the value x is equal to 0, which gives us 82. Therefore, the y-intercept is at 0, 82. To find the x-intercept is a bit trickier, if it can be done at all. Not all parabolas have an x-intercept, and this is because a parabola might open up and simply have its vertex at a positive y value, in which case it never touches the x-axis, or it might open down and have its vertex at a y value which is negative, in which case it still never quite gets to the x-axis. So these would have no x-intercepts, but sometimes they do. Sometimes they have 1 if it just barely touches. Sometimes they have 2 if it crosses. To find out whether or not it does, we should set the function equal to 0 and solve. Since this is already a perfect square, x plus 4 squared here, it's most simple to solve for x by inverse operations. We move the 50 over, we divide by 2. We get negative 25, and notice that now that we have this negative, if I take the square root of that, I get plus and minus 5i. Now, this is going to be the hallmark of not having a x-intercept. Plus and minus 4 plus and minus 5i are not real numbers, so this thing doesn't have any intersection with the real x-axis. The x-axis is all real numbers. And this says, well, the only time this parabola is going to be 0 are at these complex values. Okay, so in that case, we are not going to see a x-intercept. This is very much akin to what we've seen before with things like x squared plus 4, an upshifted parabola, which will of course not have an x-intercept, which would have solutions to this equal to 0 at x equal to plus minus 2i, right? If we have something like that, our complex values are going to be our only zeros, and therefore we will not see an x-intercept. All right, let's move on to the next question. Same question. What is the vertex, the x-intercept, the y-intercept, etc.? So we are going to first examine the form. It's in this a times this quantity squared plus k form. So we're going to just match. And here we have a minus 4. The form is minus h. And so h is given by 4. Here we have a 25. So we have a vertex at 425. This parabola, however, opens down. So even though our vertex is at some positive value, because it opens down, we are confident that there is going to be 2 solutions for an x-intercept. For a y-intercept, we just have to plug in 0. Plug in 0, evaluate it, we wind up with 9, and so this has a y-intercept of 0, 9. But when we want to solve for the x-intercepts, we have to solve the equation 0 is equal to f of x, which is defined this way. So bringing our 25 over, dividing off our negative 1, taking the square root, plus and minus of both sides, and bringing this last term of 4 over to the other side, we get 4 plus and minus 5. 4 plus 5 is 9, 4 minus 5 is 1, and so we wind up with x-intercepts at 9, 0, and 1, 0, respectively. Now, there are a couple ways to find the vertex in this kind of a scenario. I'll begin by showing you the method of completing the square. After that, I will show you a formula which you can use to do this. But for now, let's talk about the method of completing the square as it relates to things which have a constant in front of the x squared. We've looked at completing the square before, but usually in the context where of A, B, and C in this quadratic equation here are where A is 1. Now, when it is 2, I suggest just factoring it out. So I'm going to begin by taking our first two terms and factoring out the 2 from my x squared, which gives me a negative 12 for my linear term. I leave a little space here, and then I write my plus 40 on the outside. Now we want to add the thing which will make this x squared minus 12x into a perfect square. Half of 12 squared is 36. So we want to add 36 here to give me x minus 6 squared. However, I didn't really add 36. I added 2 times 36 because this 2 out here is going to affect this 36. And so if I want to balance what I've done, I need to subtract 36 times 2 from the outside. Now 36 times 2 is negative 72, and we combine that with a 40 to get negative 32. Looking at this, now we have put it in a times x minus h squared plus k form. So we have a parabola with a vertex at 6 minus 32. It opens up, it's got a negative y value on its vertex, so we know it's going to have x-intercepts. Its y-intercepts we find by plugging in 0, which is actually most easily done to this first equation. If I plug in 0 here, these two terms go away, and I'm just left with a constant coefficient of 40. Now, either we could have solved this one set equal to 0, but I couldn't help but notice that this one actually factors pretty nicely. If I set it equal to 0 and divide off my 2, I get x squared minus 12x plus 20, which factors as follows. And so we wind up with x-intercepts at 10, 0, and 2, 0. For this one, I would do the same thing, but now our leading coefficient is a minus 2. If I factor this out, I'm going to have a x squared minus 16x for my quadratic and linear terms. And then I'm going to want to figure out what I should plug here to make it a perfect square. Now, half of this is negative 8, and squared is 64. And so I would want to add 64 to the inside. This would give me x minus 8 squared. But I didn't really add 64. I added negative 2 times 64, which is negative 128. So if I want to balance what I've done, I need to do the opposite over here. That would be the same as adding 128. Don't be confused that you added 64 here, and so you need to subtract something. You did, but if we factor out this minus 2, and I encourage you to do so to figure out easily what you need to add to complete the square, you really did add negative 128, and so you need to add positive 128 to balance it. Now, it just so happens they put a negative 128 out here as well, and so we wind up with a 0 for our k value. That means that the vertex is at 8, 0. Now, that might already tell us a little bit about our x-intercepts. But let's just note that our y-intercept, if I plug in 0 here, we get minus 128. Let's keep these signs correct, because these two terms would go to 0, and we would just be left with negative 128. The x-intercepts, well, we could either solve this one set equal to 0, but actually, in this case, I think it's going to be easiest to just set this one equal to 0, because we have our linear term already gone for us. So if I set that equal to 0, I can divide off negative 2. Well, okay, 0 divided by negative 2 is 0. Then I can take the square root of both sides, and plus and minus the square root of 0 is just 0. And then I can move my 8 over to find, yes, the vertex, right? If the vertex, and this is a downward-facing parabola, is at 8, then we know how many x-intercepts it has. It only has the 1, because the parabola doesn't cross it. It sort of bounces off of the x-axis, and so we only have this one x-intercept with even multiplicity. We'll talk more about multiplicity, and we'll talk more about its behavior at certain zeros in subsequent videos. Questions 7 to 12 ask for a more complete analysis of the quadratic equation given. They want the orientation up or down, they want the vertex, they want the y-intercept, x-intercept, they want to know if that vertex is a max or min, they want to know if what is the axis of symmetry, because all parabolas are symmetric in a line cutting through their vertex, right? They are mirror images on either side of that. And what is the graph of this? Determine its domain and range. All right, let's do all of that. So the first thing I would do with this kind of thing is put it in its standard form. And that means factoring out this -1 here so I can complete the square. I complete the square by adding 3 squared, and that will let me factor this as x plus 3 squared. Now, I added +9 on the inside, but I factored out a -1 beforehand, so really I added -9, and therefore I need to add 9 in order to balance it. -8 plus 9 is +1, and so now we know where my vertex is, and we already knew, just by looking at this leading term, that this vertex was going to be our maximum. That's because this parabola opens down, and when a parabola opens down, the vertex is its absolute maximum. We also can straight away say things like the domain, range, and axis of symmetry. The axis of symmetry for parabolas that we'll be looking at is going to be a vertical line that cuts through this particular x value. So we describe that with the line x equals -3. The domain of all polynomials, including these quadratic parabolic polynomials, is going to be -infinity to +infinity. There are no domain restrictions on quadratic equations. Then the range is determined by whether or not it opens up or down, and what is the y value of the vertex. This opens down, so this number here of 1 is its maximum, and then it goes down forever. So that will have a range, or the acceptable y values, of -infinity up to 1 inclusively. It does attain this at its vertex, so we include the 1. Now, what are its y-intercepts? Well, plugging in 0, we'll just get -8. From our standard form, it's easy to solve this for when it is equal to 0 with inverse operations. Bring the 1 over, divide by -1, take the plus minus square root of both sides, and then move our h term over here. This will give me -3 plus and -1. -3 plus 1 is -2, and -3 minus 1 is -4. So we have the following two x-intercepts. This really does give us enough information that we can go over here and graph this thing, right? We have a vertex at -3, 1. Here are my x-intercepts. Here is my y-intercept. But we already know this has no real manipulation to the slope. It's just been flipped vertically. So we could also do our over 1, down 1, over 1, down 3, over 1, down 5, and get the following points. And notice that all syncs up nicely with the points that we calculated for this problem. For the next one, we're going to repeat that process. I would divide out 3 from the first two terms. So dividing 3 out from x squared, dividing 3 out from -48, I get x squared minus 16x, and I put my times 3 up front. I leave a little space right here because I'm going to complete the square. Completing the square means taking half this middle term and squaring it and putting it inside. Half of -16 is -8, and squared is +64. Now, I didn't really add +64, I added 3 times that. So 3 times that is 192. If I added 192 right here, I'm going to want to subtract it from the outside. That's going to keep this equation balanced and make sure it's still equal to what came before. This is now a perfect square, which can be factored as x minus 8 squared, and 189 minus 192, that gives me a -3 out here. We see that this leading coefficient here, or this leading coefficient here, whichever you like, is positive, so this opens up. Therefore, our vertex will be a minimum. That vertex is at +8, -3. We change the sign of this one, we keep the sign of this one to get our vertex x and y. The axis of symmetry will be the vertical line going through this. So you'll have x equals this for your vertical line of symmetry for all parabolas that we're going to be looking at right now. The domain is always -infinity to +infinity for any polynomial, and the range, well, our lowest value, because the vertex is a minimum, is going to be this y value here. Now, we'll include all values above that, so we go from -3 inclusively up to infinity. How do we find a y-intercept? You plug in 0. Plugging in 0 here is particularly easy. You just get 189. How do you find x-intercepts? You solve when you set it equal to 0. Now, setting this one equal to 0 is particularly easy to solve. Bring my 3 over, divide by 3, take the plus minus square root of both sides, and bring my 8 over, and I wind up with 8 plus and minus 1. 8 plus 1 is 9, 8 minus 1 is 7, and so these are our two intercepts. Now, notice when we go to graph this thing, we really can't use the y-intercept. It's well off the edge of the map. And also, our trick of going up 1 and over by some odd number needs to be augmented because we've increased the slope by 3, right? Our leading coefficient here is now a 3. And so instead of going over 1 up 1, I'm going over 1 up 3. And instead of going over 1 up 3, I need to go over 1 up 9 to make those points connect. This is just a nice little trick that I like to use in order to pick my points quickly in graphing a parabola, but especially if we're scaling, if that confuses you, you can really just pick some points around your vertex and evaluate them. I also could have done 9 in here. Squared would be 1 times 3 and then minus 3 to get my 0. Or 10 in here would give me a 2 in difference from 8. Squared is 4, times 3 is 12, and minus 3 is 9 to give me this point here. You could also evaluate to find points to plot. It's just a nice fact that, you know, we're doing this over 1 up by some odd number thing, but it does require the caveat that if we are multiplying by some term up front here, we have vertically scaled the parabola, and we need to take that into account when we're doing that trick. Okay, here's another one that's already put in standard form for us. That's nice, because then we can just read off the vertex as minus 1, minus 9. Its leading coefficient is positive, so it opens up, and our vertex will be a minimum. That means that the axis of symmetry is going to cut through minus 1, so we have x is minus 1 as our equation for that line. And our domain and range, well, the domain is always negative infinity to positive infinity. The range is going to be from negative 9, our lowest point, up to infinity inclusively on this minus 9. What is our y-intercept? Just plug in 0, and we would get 1 squared minus 9. That's minus 8. What is our x-intercept? Well, we need to solve this, set equal to 0, bringing over our 9, taking the square root, plus and minus, and then minusing 1 over here. We get minus 1 minus 3, which is minus 4, and minus 1 plus 3, which is 2. That's going to give us our 2 points. And let's look at how that relates to our graph. Over here, I'm going over 1, up 1. Yes, that is our y-intercept. Over 1, up 3, over 1, up 5. Hey, there we are at one of our x-intercepts. And now we just can complete that pattern to make another point, right? This is over 1 up by the next odd. So over 1 up 5, over 1 up 7, and here's a new point. And this helps us sort of complete that picture of the parabola in a really graceful way. Next one. Okay, let's rearrange this slightly because it's a little bit out of order. Let's move this squared term up front, including its negative sign, and let's move the 4 to the back, including its positive sign. This will help us see that the vertex is at negative 2, 4, and that this sucker opens down. The axis of symmetry will be at x equals minus 2, and because we're opening down, this y value is our highest one, so our range goes from negative infinity to 4, inclusively. What is our y-intercept? Plugging in 0, we could find that as just being 0. So we know that this passes through the origin. And actually this tells us we know one of our x-intercepts here. Let's see if we find that when we go to solve. We set it equal to 0 and bring this over to solve. That's going to give us minus 4, but then dividing off our minus sign, we get positive 4. Taking the square root, plus and minus, and then bringing our 2 over as a minus 2, we have minus 2 plus 2, which is 0, and minus 2 minus 2, which is minus 4. So we do find our origin again when we do our x-intercept pattern, and graphing these points, we get a good picture of our parabola. Now notice that we're going over 1, down 1, over 1, down 3, over 1, down 5, and so on to get a good collection of points to make the parabola look right. But all of our x-intercepts and all of our y-intercepts, they sort of accord well with that trick. So we have, good evidence here that we've done this correctly. Okay, as promised, I would like to go into a little bit more detail about how we can find the vertex without having to put it in standard form. just looking at this sort of general form of the polynomial ax squared plus bx plus c, we can read off the vertex straight from this. What we must know is that the x value of the vertex is going to pertain to b and a respectively. It shouldn't really pertain to c because that's just going to vertically translate something. That wouldn't change the x value of the vertex. On the other hand, b and a, if I take negative b and divide it by 2a, this will be the value of x for my vertex. And then if I want to know the value of y, I would just plug that number into f of x and figure out what my y value should be. You might be recognizing these kind of terms from the quadratic equation. And if we took a look at the x values for our zeros, we would note that they are symmetric around the vertex. That is to say, they are in equal spacing up and down from the vertex. And what do we notice here? That we're talking about some value minus b over 2a. One of them is going up by some amount, and the other one is going down by the same amount. So this term here, if I call this, I don't know, d, we're going up by d here and down by d here. So how do I make sure that my zeros are symmetric around the vertex? I go up and down from the vertex by d. So this tells us that the vertex will be in the center of the zeros, and that's this value right here. This is negative b over 2a as far as an x value is concerned. There's also some interesting patterns we could notice if we plugged this in to f of x. Substituting would look like this, and getting like bases so that I could combine my terms, we could get the following formula for y. I don't encourage memorizing that formula per se. I would rather each time just sort of plug this value into f of x, because why should we memorize additional formulas when we don't have to? But it is interesting that we find the negative of the discriminant showing up here. Something we saw in the quadratic equation actually does show up in the formula for the y value of the vertex. So now let's see what we're supposed to do with that information. They ask us to sort of characterize whether or not it's going to have a absolute max or min at its vertex, and what is the location of that max or min, and what is its value. Then we can find the domain and range of f pretty easily. Here we have a equals 1, b equals 6, so negative b over 2a is minus 3. If we plug that into the function, we find 17. And so our vertex will be at minus 317. Noting that this is positive, and so the parabola opens up, our vertex is a minimum, and so the range is going to go from 17 inclusively up to infinity, because 17 is the smallest value. Now, the domain for all of these quadratic equations are going to be negative infinity to positive infinity, as all polynomials do. Here, we need to be cautious because they've scrambled the order in problem 14. We need to make sure that we recognize a is the coefficient of x squared, not just whichever one they decided to put first. So our a is 6, our b is negative 36, and if we look at negative b over 2a, we find out that that is 3. If I plug in f of 3 here, I'm going to wind up with 96, or negative 96, I should say. And so noting that this 6 is positive, we know this opens up and the vertex is a minimum. If it were negative, it would open down and the vertex would be a maximum. But now we find that the vertex is a minimum, and so we have this vertex at 3, negative 96. If negative 96 is our lowest value, we put that on the bottom here with a bracket up to infinity for our range. Same one here, we have a positive value for a, that means it opens up and the vertex is a minimum, whereas the x value of the vertex, it's going to be at negative b over 2a, or negative 12 over 2 times 16, which reduces to negative 3/8. If I plug in negative 3/8 into this function, I'm going to wind up evaluating that to negative 25/4. And so we know that the vertex is going to be at negative 3/8, negative 25/4, and the range is going to go from negative 25/4 up to infinity. 16 to 18 asks us to find domain and range for f given certain characteristics. Well, the domain, again, will always be negative infinity to positive infinity for anything that looks like this. If the vertex is here and it opens up, then negative 13 is our lowest value, and so our range would be here. If the vertex was at 5, negative 20, and a opened up, then we would find this to be our lowest value of the range. And likewise, if we were talking about an absolute minimum, that's just another way of saying that the parabola opens up. And if this is our minimum value, then our range is going to go from 30 up to infinity. I noticed that they didn't have many examples here of parabolas who open downward, where a is negative, or where the absolute maximum is a given value. All that would do is simply switch these ranges around so that you were going up from negative infinity up to some value, bracket to include it. All right, let's talk about some word problems that also use quadratic equations. One of the main ones is going to be the height of a projectile in motion over time. Projectiles in motion are subject to the constant acceleration of gravity when we're near the Earth's surface, and it turns out if we ignore air resistance, these kinds of curves are well fitted by a parabola. So if this parabola, negative 16t squared plus 120t plus 64, gives the ball's height above the ground in feet t seconds after it was thrown, we can answer the following questions just using the geometry of the parabola. I want to notice that even though they don't ask about it, we could easily figure out what the initial height of the ball is. At time 0, it's at 64. So this person was at a 64-foot building, and that's why the 64 appears here. After how many seconds does the ball reach its maximum height? Okay, so what we need to know to get this 3.75 is that the vertex is the max. The vertex will be at negative b over 2a, and that means negative 120 over 2 times negative 16, which we can simplify to 3.75. This will give us the time at which it reaches its maximum height. How do you find its maximum height? Well, you just plug in 3.75 into the equation and evaluate. And it turns out that's going to give us exactly 289 feet. How many seconds does it take the ball to hit the ground? Well, hitting the ground means being of height 0. So you take the equation and set it equal to 0 and solve. I actually think this is easiest to do if we just plug these numbers into the quadratic equation, and I've skipped that work here. If you want a review on that, you can go back and check out the videos on the quadratic equation. So plugging into the quadratic equation with a equals minus 16, b equals 120, and c equals 64, we get these two values of negative 1/2 and 8. Now, negative 1/2 isn't a real solution. That's popping up because we are talking about a parabola which starts at some height and then goes down. Now, if we looked backwards in time, the parabola that traces out would also hit the ground at a certain time, but we're not actually talking about that. So our model here is only good for positive time. Before that, there's a curve that describes it, but the ball really didn't do this. So usually when we're dealing with these physics problems, these sort of negative time solutions don't count, and you only want to take the positive solution of positive 8. For the next problem, we want to find the dimensions of a rectangle with a certain perimeter and a maximum area. So what we want to do to figure this out is write down the equation for the perimeter of some rectangle. Rectangles have a length and a width, and their perimeter is going to be adding up all 4 of these sides, which are 2 of these lengths and 2 of these widths. So if we know that's 640, we could actually solve for one of the variables in terms of the other. That would give us 320 minus the length is equal to the width. Now, what about the area? Well, area is length times width. And substituting in what we just learned about width, which is that it's 320 minus L, we see that we actually do get a kind of parabola. We get negative L squared plus 320L. So this is an equation for the area just in terms of the length, given that we have this constraint of 640 on the perimeter. Now, how do we find out where this area is going to be maximum? Well, since it's a parabola, we know that its maximum is going to be attained at its vertex because this is a parabola opening down. So if I took a look at that value, it will happen at negative b over 2a. And so at negative b over 2a, we get a value of 160. Plugging that back into the equation we had for W, which was 320 minus L is equal to W, we get, well, 320 minus 160 is 160. And what does that tell us? It tells us that the rectangle that has maximum area is going to have length 160 and width 160. In other words, it's a square. And it's kind of an interesting fact that the rectangle that maximizes area is a square, given that we are including all the sides here. So we're going to see an example of that what happens when we don't include one of these sides, what then about the maximum area in just a moment. But for right now, let's address this next problem. This gives us another equation for some position and height of a projectile. We know that the vertex will be maximum, so finding out because this is opening down, so finding out where is that vertex in terms of t, we plug in these numbers into our negative b over 2a to get 11.429 approximately. This is actually going to be a long repeating decimal here, but out to 3 decimal places is as follows. If I wanted to solve for peak height, I would substitute this 11.4 value into our equation. And if you use enough decimal places, meaning if you take this out to a great deal, don't plug in your approximate value here, plug in the whole thing. Plug in this if you have to, but if you plug in enough decimal places, what you'll find is we're actually going to get a whole number value here of 846. Finally, to figure out where it would achieve splashdown, in other words, where is its height going to be 0, we're going to want to plug in these values into the quadratic equation. And especially because we're using these nasty decimals here, I wouldn't try to factor this. I would just plug it into the quadratic equation and solve. I'm skipping the work on that here, but we will wind up with negative 1.7111 and so on, and 24.5683 and so on. Now the negative time solution should be discarded as discussed, and the only real solution is going to be 24.568 rounded to 3 decimals. Here we have one of my favorite problems involving a parabola. It says that someone wants to build a pen for their farm animals. One side of that pen is going to be up against the side of a barn, so they don't need fence on that side. Now, so we have a rectangle, but now with only 3 sides that we need to build. So our perimeter of that rectangle is going to be 2 of these plus 1 of these L's. And that, we only have 500 feet of fencing, so the sum of those must be equal to 500. And we want to build the biggest pen that we can for our animals in terms of area, so we want to maximize this equation of length times width. Well, length was 500 minus twice width. So taking the product of these and rearranging, we wind up with minus 2w squared plus 500w. This is a downward facing parabola, and so we can maximize it by finding its vertex. If I plug in negative b over 2a, I will get negative 500 divided by minus 4, which is positive 125. So we found the width that gives maximum area. Now plugging that back into our equation for L, we find 250. So our dimensions of this are going to be 125 by 250 to give maximum area given the constraints. Our area then will be the product of those two things, which is 31,250 square feet. For this last question, we're going to want to find the equation for a quadratic function who has a vertex at a certain point and that passes through another point. So noting that this is our vertex location, we want to plug that into the formula that shows us the vertex h and k straightforwardly, right? That's going to be minus h, where h is 5, so we put a 5 here. And then we're going to want to add k, so that's going to be putting an 8 here. Now, the only thing we don't know is what this a should be in order to make that happen. If we plug in 2 into this equation, we will get minus 8. And so let's see what that looks like when we plug in 2 into the form of the equation. We'll have a times 2 minus 5 squared plus 8. Now, if I bring this 8 over, I'll get minus 16 is equal to a. This 2 minus 5 is negative 3, but squared, that's going to be 9. So we find out that we're going to need negative 16 over 9 for a value of a. And that was the only parameter left that we had to figure out. We now have the complete form of this quadratic equation. We're going to have negative 16 over 9 times x minus 5 squared plus 8. And that's going to do it for this problem and also for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.